Section: Introduction. In this section, we introduce the self-attention mechanism at the heart of the transformer architecture, which enables the model to prioritize different parts of the input sequence when creating representations. Since transformers do not inherently account for the order of inputs, adding positional information is vital for understanding language's sequential nature. Initially, fixed sinusoidal encodings were used, but more recent approaches, like Rotary Positional Embeddings, (ROP), utilize rotation matrices applied directly to token embeddings, allowing for position-dependent rotations that encode each token's position through phase shifts in the embeddings. While ROP has proven effective, its effects on the internal workings of transformer models, especially regarding its interaction with nonlinear components like feed-forward neural networks, FFNs, and self-attention, have not been thoroughly examined. Understanding this interaction is crucial for grasping how transformers manage and retain sequential information, which is important for tasks that require detailed temporal modeling. Our research focuses on three key areas: the spectral properties of ROP, its interactions with nonlinear activation functions, and the emergence of interference patterns due to phase alignment. Our main contributions include 1. A comprehensive analysis of ROP's influence on the model's internal behavior and positional dependency, and 2. An exploration of how nonlinearities in transformers interact with ROP to create complex frequency patterns. In the related works, we note that the transformer architecture transformed sequence modeling by using self-attention, eliminating the need for recurrent structures. The original transformer incorporated sinusoidal positional encodings to indicate token positions. Subsequent advancements included relative positional encodings, which improved generalization across different sequence lengths, and the transformer XL, which enhanced long-term dependency capture. The music transformer also utilized relative positional encoding for music generation tasks. ROP introduced relative positional dependence through phase shifts while maintaining inner product structures, allowing for better generalization to longer sequences. We also highlight that nonlinear systems, such as feed-forward neural networks with activation functions like ReLU or JLU, can create higher-order harmonics and exhibit frequency mixing. Concepts like constructive and destructive interference, which describe how overlapping waves can amplify or diminish signals based on their phase alignment, are relevant here. Researchers have begun to apply signal processing principles to analyze how frequency components and phase relationships influence neural network behavior. In our methodology, we combine theoretical analysis with empirical experiments to investigate how ROP affects transformer models. We conducted experiments using autoregressive transformer models, specifically Llama 2, Llama 3, and Llama 3.1, focusing on Llama 3 for our primary results, with additional details in the appendix. Our experiments aim to understand how phase shifts from ROP impact the model's internal dynamics through two main approaches. In the first set of experiments, we manually applied phase shifts to the attention mechanism by rotating embeddings extracted from the models. We used 1,000 text samples, each with 200 tokens from the book corpus, to analyze how these shifts affected attention scores. The second set of experiments examined the effects of phase alignment and misalignment on FFN activations. We created synthetic sequences to isolate the impact of input structure on phase interactions, using repeated identical tokens to promote phase alignment and alternating tokens to encourage phase misalignment. We measured differences in activation patterns using metrics like variance, kurtosis, entropy, and the number of activation peaks. All experiments were conducted on Google Colab Pro with NVIDIA A100 GPU, utilizing the Hugging Face Transformers library. Section Summary. In this section, we explore the significance of Rotary Positional Embeddings, ROP, in transformer models, focusing on how phase shifts introduced by ROP affect the internal dynamics, particularly in self-attention and feed-forward networks. We conduct experiments to analyze the impact of these phase shifts on attention scores and activation patterns, aiming to deepen our understanding of how transformers process sequential information. Section: Spectral Properties. In this section, we explore the spectral properties of ROP, which applies a rotation to embedding vectors based on a frequency for each dimension. For a given position, the embedding is rotated, and we can analyze the rotation matrices by looking at their eigenvalues. These eigenvalues indicate the frequencies at which the embeddings are adjusted due to positional encoding. By calculating these eigenvalues, we gain insight into how rope introduces phase shifts that change with position, effectively embedding positional information. Since these are rotation matrices, their eigenvalues lie on the unit circle in the complex plane, meaning the rotation keeps the size of the embeddings the same but changes their phase. This rotation creates oscillatory behavior in the embedding space, which can be broken down into frequency components. To better understand how rope influences the behavior of embeddings in transformers, we examine the eigenvalues of the rotation matrices used in positional encoding. While we know that rotation matrices have eigenvalues on the unit circle, analyzing them in the context of rope reveals significant effects on the model's ability to handle time-related dynamics and memory retention. We consider a 2D rotation matrix for a specific dimension, where the eigenvalues satisfy certain conditions. These eigenvalues also lie on the unit circle, indicating that the rotation from rope causes the embeddings to oscillate at a frequency determined by the frequency parameter, with the phase changing linearly with position. This analysis shows how the choice of frequency affects the model's sensitivity to changes in position. As the sequence progresses, the embeddings continuously rotate in their respective 2D subspaces. The linear phase change means that embeddings at different positions have different phases, leading to oscillatory behavior that impacts how the model processes sequential information. The differences in phase influence the attention calculations, resulting in either constructive or destructive interference patterns. The frequency parameter determines how quickly the phase changes. Smaller values lead to slower changes, allowing embeddings to remain similar over longer distances, which corresponds to better memory retention. In contrast, larger values result in quicker phase changes, focusing the model on short-term dependencies. By adjusting the frequency, we can control how long the model retains information, which is crucial for tasks like language modeling or real-time translation. In transformer models, rope alters how positional information is integrated by applying a rotation matrix to the queries and keys at each position. The attention score between two positions depends on their relative position, and the rotation introduces a phase shift that affects the alignment between the queries and keys. As the distance between positions increases, the phase difference grows, which can reduce the attention score due to misalignment, effectively incorporating relative positional information. The relationship between the positional difference and the frequency plays a crucial role in the similarity between embeddings. When the positional difference multiplied by the frequency is close to pi, the cosine of this value approaches -1, leading to interesting behaviors in how tokens at different positions are compared. When tokens are close together, their embeddings are highly similar. As the positional distance increases, the similarity decreases, and once the product surpasses pi/2, the cosine becomes negative, resulting in unexpected behaviors where similar tokens may not align as intended. To ensure that the cosine function behaves predictably, we need to limit the range of the positional difference multiplied by the frequency. We observe that embeddings with smaller frequency values maintain higher similarity over longer distances compared to those with larger values. Section Summary. In this section, we analyze the spectral properties of rope, which applies rotation to embedding vectors based on position, affecting their phase and oscillatory behavior. We find that the choice of frequency, θ_k, influences the model's sensitivity to positional changes, impacting memory retention and the decay of similarity between embeddings as positional distance increases. Section: Constructing the memory function. In this section, we analyze how rotary position embedding, ROP, affects our model's ability to remember information over time by examining the memory function, which reflects the cumulative impact of past inputs at a certain lag. ROP adds cosine variations to the attention mechanism, allowing us to approximate the memory function. Here, the frequency components introduced by ROP are represented as theta, while the weights that show how much each frequency contributes are denoted as alpha. The attention score between two positions is influenced by the cosine of the product of theta and the lag, indicating that the effect of earlier positions on the current position oscillates and diminishes based on these frequencies. This setup resembles a Fourier series, where the memory function captures the combined effects of past inputs as a mix of oscillating components. The frequencies and weights determine which time-related frequencies are highlighted or reduced as information moves through the network. If the weights decrease for higher frequencies, we find that the memory of older inputs fades more quickly. These weights can be affected by both the attention mechanism and the transformer's natural frequency response, potentially changing across layers as the model adjusts its focus on different frequency components during processing. We view the attention mechanism as a form of temporal filtering and derive the memory function using Fourier analysis. We break down the input sequence into its frequency components, where the Fourier coefficients represent the contributions of each frequency. The attention mechanism modulates these components using cosine functions, leading to a memory function that reflects the cumulative influence of past inputs, shaped by the frequencies introduced by rope. The cosine terms indicate that the memory function oscillates over time, with its characteristics determined by the frequencies and weights. In transformer models, the attention mechanism selectively enhances or diminishes various parts of the sequence based on learned weights, allowing us to focus on relevant information. When we combine this with rope, the interaction between phase shifts and nonlinearity creates complex dynamics where certain frequency components are either amplified or suppressed. Rope applies a rotation to the embeddings based on the token's position, affecting how the attention mechanism responds not only to the content of the tokens but also to their relative positions. We compute the attention score between two positions using the rotated query and key vectors, which shows that the score is influenced by the relative position. This modulation introduces an oscillatory behavior, where the dot product of the query and key vectors is affected by the cosine of the relative position. The rotational modulation creates a frequency-based filtering effect, leading to higher attention weights for certain phase differences and lower weights for others. To explore how these phase differences impact the attention mechanism, we plotted the attention scores against the cosine of the phase difference between token embeddings. The results show a peak when there is no phase shift, indicating that the model gives the most attention when the phases align. As the phase difference increases, the attention scores drop sharply, highlighting the model's sensitivity to even slight phase misalignments. We also examined the relationship between attention scores and positional differences. The highest attention scores occur when the positional difference is 0, and they decrease quickly as the distance increases. This suggests that our model primarily focuses on nearby tokens, which is beneficial for tasks like time series prediction, as it allows the model to concentrate on periodic patterns in the data. By adjusting the frequency parameters, we can enhance the model's sensitivity to specific frequencies, improving its ability to predict future values based on historical trends. Section Summary. In this section, we analyze how rotary position embedding, ROP, affects the model's memory function, showing that it introduces oscillatory behavior in attention scores based on relative positions and frequency components. We find that the model prioritizes local context and is sensitive to phase differences, which enhances its ability to capture periodic patterns in time series data. Section: Interactions with the softmax. In this section, we explore how interactions with the softmax function influence attention weights. We compute these weights using the softmax function, which is very responsive to changes in attention scores. The oscillatory terms introduced by rope can either enhance or diminish these scores based on their positions and frequency parameters. Even small adjustments in the attention scores can lead to notable changes in the attention weights, affecting how different positions contribute. To understand the impact of the softmax function's nonlinearity on frequency components, we can expand it around the average attention score. The first term in this expansion captures the linear relationship, maintaining the original frequencies from rope. The second term introduces nonlinearity by squaring the input, which can create new frequency components that are multiples of the original frequencies. Higher order terms can lead to even more complex interactions, mixing frequencies and generating new components not present in the original signal. The softmax function acts as a nonlinear transformation that highlights significant attention scores while downplaying less important ones, similar to a resonance filter that amplifies certain frequencies. This shapes our model's sensitivity to specific positional relationships. Next, we discuss interactions with the feed-forward neural network, FFN, that follows the attention mechanism. The FFN adds more nonlinearity to the process. It takes the output from the attention mechanism, which has already been modulated by rope, and applies weight matrices and a nonlinear activation function. This activation function further alters the input, affecting the frequency components in various ways, such as generating higher-order harmonics, distorting the waveform, and introducing phase shifts. We represent the rope-modulated output for a token at a specific position, where rope introduces phase shifts. The first layer of the FFN mixes these phase-shifted components, and the weights interact with the rope-induced shifts, leading to frequency mixing. This means that tokens at different positions contribute differently to the activations based on their phase alignment. After the linear transformation, the output goes through a nonlinear activation function, which can generate new frequency components. For instance, when we apply ReLU to oscillatory inputs, it clips negative parts, resulting in higher harmonics. This allows the FFN to capture multi-scale dependencies in the sequence. We also observe that rope causes embeddings at different positions to oscillate with varying phases, leading to constructive or destructive interference. Constructive interference amplifies the output when phases align, enhancing certain connections, while destructive interference can suppress irrelevant tokens. We can analyze this interference using trigonometric identities. When two phase-shifted components combine, they create a new oscillation whose frequency is the average of the original frequencies. If the frequency difference is small, the signals reinforce each other, resulting in a stronger combined wave. Conversely, a large difference leads to alternating interference, affecting activations in the FFN. This behavior makes the FFN sensitive to positional information, allowing it to selectively amplify or dampen features based on token positions. This capability is crucial for tasks that require understanding multi-scale dependencies, such as language modeling, where capturing harmonics improves the representation of positional information. Section Summary. In this section, we explore how the softmax function's nonlinearity and the feed-forward neural network, FFN, interact with rope-modulated attention outputs, leading to frequency mixing and positional sensitivity. We find that these interactions can amplify or suppress specific frequency components based on phase alignment, enhancing the model's ability to capture multi-scale dependencies in sequences. Section. Second linear layer. Projecting higher-level features. In this section, we discuss the second linear layer, which projects higher-level features. After applying a nonlinear activation, we pass the output through this layer, denoted as W2. This layer maps the nonlinear activations back to the original embedding space or to a compatible space for the next layers, effectively projecting the higher-level features extracted by the feed-forward neural network, FFN. The input, Z, P, includes both the original frequencies influenced by rope and the higher-order harmonics created by the nonlinearity. W2 acts as a frequency-selective filter, deciding which features to carry forward. Two main effects occur in this layer. First, frequency selection, where W2 can highlight certain frequency components, like fundamental frequencies or specific harmonics, while reducing others. This helps the FFN concentrate on the most relevant temporal or positional dependencies for the task. Second, we achieve higher-level feature representation, as the second linear layer merges frequency-modulated features into a representation that captures both content and position information, which is essential for managing the sequential nature of data in autoregressive transformers. Our analysis reveals that the rotation matrices used in rope introduce specific phase components into the token embeddings, resulting in oscillatory behaviors with distinct frequencies. When these frequency-modulated embeddings interact with the nonlinear activation functions in the FFNs, they generate higher-order harmonics due to the introduction of new frequency components. This interaction leads to patterns of constructive and destructive interference based on the phase alignment of the embeddings. Constructive interference boosts neuron activations, enhancing the model's attention to important positional patterns, while destructive interference can weaken the model's ability to capture certain dependencies. We can liken ROPE to frequency modulation, FM, as it adjusts the phase of embeddings based on positional information, enriching the representation space and allowing the model to capture positional nuances. The attention mechanism and FFNs function as nonlinear filters that shape the frequency content of these modulated signals in a context-sensitive way, emphasizing or reducing specific components based on the model's learned parameters. The creation of harmonics through these n-online-arities broadens the signal's frequency spectrum, enabling the transformer to represent more complex patterns and effectively capture long-range dependencies. These dynamics improve the model's ability to adjust its focus dynamically, responding to the context and varying sequential dependencies in the input data.